Okay, so let's get started. Since you wanted me to continue, I will continue. But we have only 25 minutes, which means that we're going to cover only the summary part. This may be good actually, then you can get a chance to think about what we've discussed, so that we can have a better discussion next week in terms of strengths, weaknesses, ideas, ... Does that sound good? Okay. Next paper I chose is also my paper. I'm happy to choose these. This makes my life easier, clearly. But it also makes me give you a historical perspective in a much better way, right? And these are... Okay, this is the paper. It was published in Micro 2011. This is joint work with Penn State and Microsoft Research. Okay, so let's start. It's called Application-Aware Memory Channel Partitioning, and I'm borrowing slides from my PhD student Lavanya's presentation at Micro. So we're going to follow the same structure exactly, although we may have some slight changes. Different parts may be at different lengths. So this is also tackling the main memory as a bottleneck. This thing has a mind of its own. It has these things that no one should ever use, in my opinion, which is really play the narratives. Do you know what that is? It automatically changes the slides on you. I don't know why it does that. Let me see. I cannot see anything. Okay, slideshow. Okay, play narrations, use timings. Never do that. Okay, that's much better. I'd rather control things from here than... Okay, so this paper also tackles a memory bottleneck problem. Main memory latency is long, and because of that long latency, the core stalls and performance degrades. And when you have multiple applications, they share the main memory. And there's inter-application interference happens because of this, and many of you know this very well. The applications request interfere at the main memory, and inter-application interference degrades system performance by delaying some applications or all applications requests. And the problem becomes more exacerbated as the number of cores increases, as the memory bandwidth doesn't scale up with the number of cores. So you know this very well, hopefully by now. So the goal of this work is to mitigate inter-application interference. And the predominant approach so far, while the paper was written, was doing request scheduling in an application-aware manner in the memory controller. This paper proposes two different approaches. One is doing partitioning the memory channels across different applications to isolate or minimize interference. And it also finds out that partitioning and scheduling can go well together if they're combined in a nice way. So the second approach is to integrate memory partitioning and scheduling. And this is the very high-level key idea. Let's go through some background. You already know a lot of this. Basically, main memory consists of banks, and the bank consists of rows and columns, and you have a row buffer. And if you want to access some data in a row buffer, you need to activate the row. And existing systems use first ready, first come memory scheduling policy. They prioritize row buffer hits over others and older requests over others, all else being equal. And as a result, these are unaware of inter-application interference. Clearly, an application that has high row buffer locality can deny service to others. An application that generates a lot of requests comparatively to other applications can deny service to others. So the novelty of this work is, compared to this previous approach, is to propose a new approach that is different from request scheduling. So let's overview the previous approach first. Previous approach is making the memory scheduler aware of the applications. So memory scheduler monitors the application characteristics. It ranks the applications based on memory access characteristics, and it prioritizes the requests at the memory controller based on that ranking. Let's take an example. This is the most closely related work that the paper later compared to. This is also our work, thread cluster memory scheduling. The idea is this, basically. You have threads in the system. These are hardware threads. And the memory controller classifies them as memory non-intensive and memory intensive, and forms two clusters, non-intensive and intensive. There are some heuristics in terms of how the classification is done. And the non-intensive cluster is prioritized over the intensive cluster because these applications are generating memory requests not so frequently. And if these are prioritized over the intensive cluster, they're not going to deny much service to the intensive cluster because their requests are not as often. And also, if they don't get prioritized, they actually get denied service, assuming the first ready, first come scheduling policy, because these intensive applications generate a lot of requests. And if these applications don't get prioritized, they will get delayed behind a queue of many requests that are coming from these intensive applications. That's the insight in this prior work. And this work will utilize that insight partially to do something different. So this prior work proposes prioritizing this in non-intensive cluster. Within the non-intensive cluster, it gives higher priority to applications that are least intensive, because those are the applications that don't generate a lot of requests. Again, if you service that application's request, the application continues progress in its core. The goal is to maximize core utilization. And within these high priority within these intensive applications, the prior work realizes that you need to be very careful, because these are all very heavy applications. Think of these as elephants. I think of these as mice, and these are elephants. You definitely don't want mice to be killed by the elephants stomping the mice. That's not a good thing. That's why prioritize the mice. They're not going to hurt the elephants that much. Of course, if you go to the extreme, they might hurt the elephants also, but in general, we see that they don't hurt the elephants as much. An elephant hurting mice is more common case. But you need to be very careful in terms of how you schedule the elephants, because elephants can kill each other also. So in this case, basically, the paper proposes fair scheduling. Not exactly round robin, but it's kind of like a weighted round robin mechanism. You need to read the paper for more detail to do the scheduling between the elephants, the intensive applications. And that's the approach taken by prior work. Clearly, this adds a lot of complication to the memory scheduler, but there's advantages. It reduces interference between applications by doing this request reordering in an application-aware manner. It improves system performance. This paper actually shows that it significantly improves system performance. It also improves fairness. The disadvantage is that it requires significant modifications to the memory scheduling logic to enable this ranking, this clustering, and this prioritization that we've discussed. As you can see, there needs to be a lot of hardware machinery for this. And also, there's one other disadvantage that this paper that I'm going to describe is going to tackle. It cannot completely eliminate interference by request reordering. Fundamentally, request reordering really can reorder requests and delay interference, but interference is felt at some point. You cannot completely eliminate interference between two different applications. Okay, so the key approach of this work is to partition the memory channels across different applications. That's the idea. So let's take a look at what this means. The observation this paper makes is that modern systems have multiple memory channels. You can see that there are multiple memory controllers. In this case, we're going to look at two applications over here, which is kind of like one of the best cases. And there's a new degree of freedom that's provided by these multiple channels, which is the mapping of data across these multiple channels, right? So in current systems, data mapping or allocation of memory pages across different channels are done in an application-unaware manner. Meaning, the red application's memory pages can be allocated from this memory controller or this memory controller, or memory channel or that memory channel. And the blue application can also be allocated in both. So this causes interference between applications' requests, and you can solve the problem in the memory controller. But the solution that this paper is going to explore is to partition the channels between different applications. So if you actually allocated pages only from this channel to this application and allocated pages only from channel 1 to this application, you would completely eliminate interference. Of course, now there are questions as to what if you need more pages to this application, right? We will probably tackle that in a little bit. So this completely eliminates interference between different applications' requests. And we're going to exploit that ability to completely eliminate interference. So this is the overview of memory channel partitioning. The goal is not to completely eliminate all the interference. The goal is really to eliminate harmful interference between applications, because some interference will have to be there, because you don't have only two cores and two channels, right? Normally in systems you have many cores and a smaller number of channels. The key is finding applications that harmfully interfere with each other and segregating them to different channels. So the basic idea is to map the data of badly interfering applications to different channels, and there are two key principles that this work exploits. And these are based on prior work, but this work puts them in a nice way. Basically, it's the key idea is to separate applications that are widely different intensities in terms of memory access. Basically, separate the elephant and mice from each other. The second one is to separate the applications that have high row buffer locality from those that have low row buffer locality, because these are the ones that interfere badly with each other. An application that has good row buffer locality streams through memory. Ideally, you would like to prioritize those requests quickly, but if you prioritize them, you cause interference to the other application that doesn't have good row buffer locality. So why don't you separate them to different channels, so that all the ones that have bad row buffer locality have bad row buffer locality in this channel, all the ones that have good row buffer locality have good row buffer locality in this channel. They take turns exploiting the row buffer. That's the idea. So let's take a look at the key ideas in a pictorial way. Basically, We want to separate applications by memory intensity into two different channels. High memory intensity application interfere with low memory intensity application in shared memory channels. Pictorially, if you do conventional page mapping, red application may have some requests. This is a timeline of the number of requests that are going to be serviced by two different applications, red and blue. Red application spreads its requests to multiple channels, as you can see. And this is the timeline of servicing of the requests. Blue application happens to be low memory intensity. Red application is high memory intensity. And blue application gets delayed behind 3 requests of this red application in this channel, as you can see. And that happens to be the case. But if you do channel partitioning, in the best case, this is what you would get. Basically, red application only uses this channel, blue application only uses this channel. As you can see, both of the applications benefit in terms of performance here. Well, this is the nice case. This application clearly saves a lot of cycles to service its very few requests, in this case only 1 request. And this application also gets some saved cycles because its requests are not delayed in this bank 0, which happens to be heavily contended in this case. Of course, it's a made-up example. It's a cooked-up example to motivate a point. Right? Real systems show all sorts of behavior, depending on how you do the randomization functions, depending on how you do the scheduling. But this is a potentially realistic case. And it motivates the channel partitioning. So that's the first key principle. Map data of low and high memory intensity applications to different channels. The second principle is also intuitive, I think. High roboflow locality applications interfere with low roboflow locality applications in the shared memory channels. This is because we use the roboflow hit first memory scheduling policy. Remember, one goal of this paper is not to change the hardware much, not to change the memory scheduling policy much. So if you look at the conventional page mapping, this may be, these are the requests that are in the request buffer. And these are the different rows that the requests access to. Look, you can see that the red application has high roboflow locality in this case. The blue application doesn't have roboflow locality in these requests. And the memory scheduler reorders the request of the red application over the blue application, such that it exploits the roboflow locality in the row that's opened, R0 in this case. And this is the time units that you get with conventional page mapping. Now, if these applications were mapped to different channels, this is one potential timeline you could get. As you can see, the red application doesn't, its performance doesn't degrade. You can still exploit roboflow locality here. And the blue application's performance improves because it doesn't get delayed behind the requests of the red application. Now clearly, the impact that is shown over here is limited by the width of the slide, because you might imagine 100 requests of red application going to row 0, right? So you could actually save a lot more cycles than what is actually shown in the slide if the roboflow locality of this application is very large, as well as intensity is very large. But you could imagine this case happening between 2 very highly intensive applications. One of them has extremely good roboflow locality. One elephant has very good roboflow locality. Another elephant has very bad roboflow locality. The elephant that has good roboflow locality will deny service to the elephant that has very bad roboflow locality. Instead, we could eliminate the interference between the elephants by mapping them to different channels. Okay, that's the second key insight. Map the data of low and high roboflow locality applications to different channels. Okay, so those are the key insights. Now the question is, how do you actually put them to work? And now that leads to the mechanisms in some detail. Let's take a look at the mechanisms. I should speed up a little bit. Basically, this is a hardware-software cooperative mechanism also. Hardware provides profiling, and you need to classify applications into groups. You need to partition channels between the application groups, assign a preferred channel to each application. So it's not a hard partitioning mechanism. It's important to realize that. If you do hard partitioning, you run into memory capacity issues. Because if you do hard partitioning, you cannot allocate memory anymore from this channel, and the channel is full. And if you don't allow an application to be allocated memory from some other channel, now you get a page fault. Now you need to actually pay a lot higher cost. That's not the proposal of the paper. That's very bad, I think, in general. So the paper is still flexible. It tries to minimize the overhead that it introduces by assigning a preferred channel to each application. And if enough pages are not available in that preferred channel, then you allocate from some other page. And actually, the paper proposed a page replacement policy. And actually, there are potential research that could be done in page replacement policies for this, which is not covered in the paper. And then the next step is to allocate application pages to the preferred channel as much as possible, without, of course, getting into page faults. So this is a part that's done in hardware only, profiling part, because you need some specific performance counters for this that don't exist in real systems, or that is not fully at least. And this is the part that's put into system software in the paper. But of course, you can imagine doing all of this in hardware. And if the counters already exist, you could imagine doing all of this in system software potentially as well. So okay, let's take a look at these steps in relatively some detail. Hardware counters collect application memory access characteristics, and as I mentioned, there are two key things that are to be considered. Last level cache misses per kilo instruction, that's the memory intensity metric that's used in this paper. It's not the only metric, but this is a good metric that the paper proposes. Row buffer locality, row buffer hit rate, the percentage of access that hit in the row buffer. You could imagine other metrics, and we could actually go into a rat hole in terms of the metrics. While doing the research, actually, Lama looked at many different metrics with the collaborators. The second step, once you know the information about the application, you classify them. The first step is to test the intensity. The application is classified as low intensity if this is low. It's classified as high intensity if it's high. And for low intensity applications, we don't care about row buffer locality. At least that's the empirical results show. For high intensity applications, we further classify applications into high intensity low row buffer locality and high intensity high row buffer locality, because this is where interference really happens between the row buffers a lot. Once you segregate applications between low intensity and high intensity, within this cluster, you don't get a lot of interference because these are low intensity to begin with, assuming you did this clustering correctly. Okay, now the next step is to partitioning the channels among groups. Clearly, you have many applications over here, and you have fewer number of channels over here. Then the question is, how do you allocate applications to the channels? And the paper proposes some allocation mechanism. It first assigns number of channels proportional to the number of applications in each group, low intensity, high intensity, basically each of these three groups. So it first allocates low intensity applications, and then it allocates these two different ones. And within these two, it assigns a number of channels proportional to the bandwidth demand of the group, so that it doesn't cause a lot of bandwidth imbalance. Because once you start partitioning channels across different applications, you may start causing bandwidth imbalance, right? In fact, that's one problem with the low intensity applications over here. Because you want to protect these applications, you want to assign enough number of channels to them, but they're not, by definition, they're not utilizing the bandwidth really well. So you're clearly causing some bandwidth imbalance in the system. But the paper shows that that's a reasonable trade-off. You're basically wasting some bandwidth, but you're improving the interference in the system. And then you assign proportionally to, but you don't want to cause a lot of bandwidth imbalance over here, because these are really bandwidth sensitive applications. Okay, so there's more, and then the next step is partitioning channels among groups. There's another step to finish this. Now you have three types of channels. And then the next step, assign each application a preferred channel from its group's allocated channels. And the paper proposed another heuristic. It distributes applications to channels such that group's bandwidth demand is balanced across its channels. So let's take a look at low intensity applications, channel 1, channel 2. If you have three applications, MPKI 1, 3, and 4, this is what we try to do. It's a heuristic, again, right? It's not perfect. Basically, we try to equalize the sum of MPKIs across different channels. And then the next step is to enforce channel preferences computed in the previous step. On a page fault, the operating system allocates page to the preferred channel if there's a free page available in the preferred channel. Otherwise, it doesn't do a hard partitioning. The replacement policy tries to allocate a page to the preferred channel. And if it fails, it allocates page to another channel. So we slightly modify the replacement policy to evict stuff from the preferred channel first. And it turns out there's a lot of slack in the existing replacement policies, page replacement policies, because you have a lot of pages in memory. And if you have a few number of channels, you can find a page that's reasonable to evict from the channel that you are preferred on. Okay, this is very interesting. I think there are a lot of interesting questions here that span across the stack clearly. And the operation of this is interval based. Basically, you have some current interval where you profile the applications. At the end of the interval, you do this classification, partitioning, and assigning of preferred channels. And the next interval, you enforce the channel preferences. So if you want to migrate an application's pages from one channel to another, you may actually want to do that over here. And the paper has some small discussion, although it doesn't talk a lot about dynamic migration in this case. Okay, so let's go back. The previous approach was application-aware memory request scheduling. The paper's approach, we've already discussed, application-aware memory channel partitioning. But the paper also realizes that it makes sense to combine partitioning and scheduling together. And the observation is this. I already said that, actually. Applications with low memory intensity rarely access memory. And dedicating channels to them results in precious memory bandwidth waste. And the paper realizes that they actually have the most potential to keep their cores busy, and you would really like to prioritize them. You don't want to dedicate channels to the lowest memory intensity applications. You would really like to prioritize them. And if you prioritize them, they interfere minimally with other applications, so prioritizing them doesn't hurt others. So the paper comes up with another category, which is very low memory intensity applications, and it basically doesn't enable them to participate in the memory channel partitioning. It doesn't allocate channels to them. It basically allocates pages to these applications from all channels, but basically modifies the memory scheduler minimally to enable the prioritizing of these applications over other applications. And for the remaining application that uses memory channel partitioning. So that's the idea. Basically, there's minimal change to the scheduler to prioritize these very low memory intensity applications because it doesn't make sense to dedicate channels to them, and it makes a lot of sense to prioritize them. Let's take a look at the results. Okay, the hardware cost first. That was one of the motivating goals, actually, because these memory schedulers are complex. Can we solve the problem in a different way? If you just do memory channel partitioning, you just need profiling counters in hardware, no modifications to the memory scheduling logic. You can keep the oldest first and row buffer hit first policy, first ready, first come, first serve. I'm not suggesting it's a good idea, but the paper shows that you could improve performance significantly over that. And it's a relatively low storage cost. If you actually integrate memory partitioning and scheduling the way proposed in the paper, you need to add a single bit per request in the memory controller, and the scheduler basically looks at that single bit to prioritize. And that's very easy to do. It's not as complicated as ranking and clustering. Let's look at the methodology. It's again in simulation, and the paper looks at an aggressive system, 24 cores, 4 channels, and you can look at the memory models. And the paper has a lot of workload categorization. It basically looks at 240 multi-programmed workloads and categorizes them based on memory intensity, and it uses some metrics. These are the works that it compares to. It compares to FRF-CFS. It compares to Atlas, which prioritizes applications with memory. These are all memory scheduling works. It compares to thread cluster memory scheduling, which we discussed briefly. I'm speeding up because we don't have a whole lot of time. Actually, 3 minutes. I think we'll be done in 3 minutes. That's good. I'm not going to go over all the results in the paper, but clearly the paper shows that as the application memory intensity increases, you get higher benefits. Not at 100% intensity. If your memory bandwidth is saturated, you get benefits, but actually we get much better benefits than memory scheduling, because if your memory bandwidth is saturated, memory scheduling doesn't help you a lot, but memory channel partitioning helps you more. But if your memory intensity levels are on the order of 50-70%, let's say 50 and 70% of the applications are very intensive, then you get a lot of the benefits during that time. If you're actually 0% of your applications are memory intensive, you don't get a lot of benefit also. But averaged across all of these workloads, these are the results that you get. Basically, the performance improvements of memory channel partitioning is significant over the best previous baseline, according to the paper. Actually, the best previous baseline is these two, but this is the best previous baseline without changing the memory scheduling logic. These are two baselines that don't change the memory scheduling logic. And if you actually change the memory scheduling logic minimally, you get 11%. So you get significant performance improvement. And compared to the best previous mechanism, which is thread cluster memory scheduling, which is complex, without changing the memory scheduling logic, you still get 1%. And if you actually add a little bit changes, very small changes to memory scheduling logic, you get a little bit more. Okay, basically at lower hardware costs, you get better system performance than the best previous scheduler. And the paper also explores interaction with the memory scheduling. Basically, it looks at, again, average across all the workloads. This is the performance of baseline scheduler, Atlas scheduler, and thread cluster memory scheduler. Clearly, you see performance benefit. This is without integrated memory scheduling and partitioning. If you actually add integrated memory scheduling and partitioning on top of each of these baselines, you get significant performance improvements. But this is actually interesting. You don't get a lot of performance improvement over thread cluster memory scheduling because it turns out, well, first of all, the first conclusion is that you improve performance regardless of the baseline scheduling policy. But the highest improvements are based on FRF-CFS because this idea is really designed with the FRF-CFS in mind. It's really taking into account row buffer hit rate as well as memory intensity. If you were designing a memory channel partitioning mechanism for some of the other schedulers, maybe this is not a great fit because some of the other memory schedulers are already eliminating interference that's happening because of row buffer hit rate and intensity. Maybe you need to take into account other considerations to do the channel partitioning on top of these other schedulers. This is actually a very interesting graph, I think. Follow-up work maybe should look at how to do the memory channel partitioning, because memory channel partitioning fundamentally needs to be integrated with the memory scheduling also, in my opinion. So that's the summary. Almost done. Uncontrolled inter-application interference in main memory degrades memory performance. Application of memory channel partitioning is proposed in this work. It separates the data of badly interfering applications of different channels, eliminating interference. And the paper also realizes that it can be combined with slight modifications to the memory scheduler by prioritizing very low memory intensity applications in the scheduler so that you don't waste memory bandwidth by dedicating channels to those applications. And all of the other applications interference is handled by the partitioning mechanism that is proposed. And the key results show that memory channel partitioning and integrated memory partitioning and scheduling provide better performance than application-aware memory request scheduling at much lower hardware cost. And that's 25 minutes for you.